All right, so this video is going to be for the complex eigenvalues case, just looking at an example. And this matrix will have complex eigenvalues. Let's just start by looking at what it does. Let me go back to my smiley face here. Let's get rid of this one. That one's done with. And I have this supply of test subjects. Let's bring in a new one. And here I'm applying the matrix 1, 5, negative 1, 5. So let's see. Okay, interesting. Something happened. Let's see that again. So let's revisit that after we get the eigenvalues and eigenvectors. All right, so start with A minus lambda identity. And we want, so the eigenvectors for eigenvalue lambda will be the null space of this. But for this to even have an interesting null space, I need to focus on choices of lambda that make the determinant of this be 0. So I want to solve this equation to start with. All right, so I typed in 1, 5, negative 1, 5, and then I subtracted lambda from the diagonals, and then I took the determinant. That's just to skip a bunch of algebra steps here. So I get the characteristic polynomial lambda squared minus 6 lambda plus 10. By the way, there are a lot of ways in Mathematica to just go ahead and skip even more quickly. There's a built-in characteristic polynomial function. But I would recommend to avoid making too big of jumps if you're using Mathematica. Or whatever other program you're using. I mean, even with Wolfram Alpha, you can just type in a matrix into Wolfram Alpha, and you just probably just be like eigenvalues on the keyboard or something, and then it'll just say, "Oh, you want to know the eigenvalues? Here they are." So that's, I mean, use that to check your work and stuff, but for your own sake, so that you get a feel for what's going on. I would recommend don't do stuff like this. I mean, do it when we're working with differential equations. Go ahead, when we're working with differential equations, go ahead and do stuff like this and just get the eigenvalues. But just for now, just for this one batch of homework problems, try to avoid doing that to get a feel for what's really going on. So by the way, I've sort of made these homework problems here 1 through 5 so that there's pretty much no repetition. Each homework problem just shows you a different situation. You know, like repeated roots where one of them is distinct roots where one of them is 0, repeated roots where there's no problem, repeated roots where there is a problem, and complex roots. So each one of them is showing you a distinct situation. You're just seeing it once. So it's worth putting in the effort to work with the numbers by hand to some extent. Stuff like this is probably totally fine. All right, so here's our characteristic polynomial, and then I could put this into Mathematica and ask it for the roots, or you can use the quadratic formula. So to be honest, I'm probably just going to put it into Mathematica and ask for the roots normally, right? And that's fine, but just this once, I'll use the quadratic formula. So negative b plus or minus square root of b squared minus 4ac 40 all over 2a. There, that's the quadratic formula. And I've got, you can see under the square root is a negative number. So this is the complex roots case. This is 3 plus or minus square root of negative 4. And let me stick the 2 inside the, let me just do that. So that's 3 plus or minus, and then this is I root 4, right? I times the root of 4, which is 2. So just I. So 3 plus or minus I, which is the same thing I would have gotten if I just said roots of this thing. Oh, I have to put it as an equation. Like that? Yeah, or maybe more familiar is just solve. So yeah, 3 plus or minus I. Now to find the eigenvectors, it's the same procedure, just now we're doing some complex algebra. So let's do one process for 3 plus I and another process for 3 minus I. And you know, sometimes it helps to number these, so maybe I can call this one lambda 1 and this one lambda 2. I don't know, it doesn't really matter. So let's work with lambda 1 and then subtract that from the diagonal. Okay, so let me just center the calculation here. So I subtract that from the diagonal and I get, let's see, 1 minus 3 plus I is negative 2 plus minus I, and then 5, and then negative 1, and then 5 minus 3 plus I, so that's 2 minus I. And I'm interested in finding the null space of this matrix. So then I'm interested in the equation, this matrix applied to x, y equals 0, 0. And then if I solve this and I get some non-zero x, y, at least one of them not 0, then that would be an eigenvector for the eigenvalue 3 plus I. So I want to solve this. Now, previously when we've been doing this, we've been noticing each time that we get, you know, one row being a multiple of the other row, so we just need one of these equations. And right now you might worry and look at this and be like, it does not look like one of these rows is a multiple of the other row, which means they're independent equations, which suggests that 0, 0 is the only solution. And you would be right to worry if that were a problem here. But in fact, we did arrange things so that the determinant of this matrix is 0. That was the whole point, right? And in case you don't believe me, here I've typed in the actual matrix that you're seeing there, and we'll type in determinant, and it really is 0. So this matrix does definitely have a non-trivial null space. We should be able to get a solution. So what gives? How come this looks like it's not, you know, one row being a multiple of the other row? Well, that's because you need to allow for, when you write down one row as a multiple of another row, you need to allow for the factor by which you multiply to be a complex number. So here it looks like if this row is to be a multiple of that row, then it would be, I guess, 2 plus I would be the factor, right? Like take this row, multiply by 2 plus I, then you would get a minus 2 minus I there. Then what would you get there? So if I take this bottom row, you don't need to do this during the calculation for any reason. I'm just alleviating the worry that it looks like this is just going to get 0, 0. So if I take this bottom row, negative 2 space 2 minus I, and then I multiply that entire row by 2 plus I, so multiply this by 2 plus I, and this by 2 plus I, then what will I get? This becomes negative 2 minus I, right? And then what does this become? So let me work this out here. I get 4 minus 2I plus 2I, and then minus I squared. But I squared is negative 1, so that's just plus 1. These cancel, minus 2I plus 2I. 4 plus 1, that's 5. Okay, so I just got 5. So this is negative 2 minus I, and this is 5. So the bottom row times 2 plus I is the top row. So these are linearly dependent rows. One is a scalar multiple of the other. It's just not as obvious because the scalar is a complex scalar. The multiplying factor you have to use is a complex number. Okay, that was a tangent. Back to the main point. The main point is because of that you only need one of these equations. So just pick one. I'm going to pick the bottom equation since that looks friendlier in terms of the minus signs. This is the bottom equation. So I can rewrite it like this. So any vector xy where the x is 2 minus I times the y is going to be an eigenvector with eigenvalue lambda 1, 3 plus I up here. So any vector where you can put anything you want for the y-coordinate, and then as long as what you put for the x-coordinate is 2 minus I times what you put for the y-coordinate, that will be an eigenvector. So we can write it like this: any scalar multiple of 2 minus I, 1. And usually we just want one eigenvector in the end. We don't need the entire infinite family, so just one non-zero one. So you can pick any number you want for y here. I like, last time when I was doing this, I picked something that helped clear some denominators out to give me a nice thing. But I think if I just pick y equals 1, then that's nice enough. So here's my eigenvector: 2 minus I, 1. All right, so there's my first eigenvalue-eigenvector pair. 3 plus I goes with the eigenvector 2 minus I, 1. By the way, it should be very easy to check your work when you're doing this. It should be that when you apply this matrix to the vector 2 minus I, 1, that you really get 3 plus I times 2 minus I, 1. Now let me do the same thing for this one. Maybe I will not show the whole process. Okay, so I subtracted 3 minus I this time from the diagonal, and I got this. So then I'm interested in solving this. And I only need one of these two equations because one of them is a scalar multiple of the other, although that's not obvious to see. And I'll take the bottom equation. So how about that's like x plus 2 plus I y equals 0. So x equals negative 2 plus I y. So I can pick anything I want for y as long as x is negative 2 plus I times that thing. And it looks like I've got just an eigenvector for the eigenvalue 3 minus I would just be any scalar multiple of negative 2 plus I, 1. Any scalar multiple. And now I just need one option for a vector, and I could pick y equals 1, but I'm actually going to pick y equals negative 1, and you will see why. I'm picking y equals negative 1, so this makes this be 2 plus I and then minus 1 here. So there's fewer overall minus signs, so that just looks prettier, but there's another reason I'm picking y equals negative 1. So 2 plus I minus 1. Okay, now let me write my summary result here. So from this eigenvalue, I got the eigenvector 2 plus I minus 1. I think I made a mistake here, actually. Yes. Looks like I missed the minus sign here. There's a minus sign here. Okay, so then there's a minus sign here. Or let me clear out that minus sign. Just put a plus sign here. So there's a plus sign here. So then there's a plus sign here. Okay, sorry about that. So 2 plus I, 1 is what I ended up with. So no minus sign here. And let's look at our overall result. So we started with our matrix 1, 5, negative 1, 5. Then we got these two eigenvalues, 3 plus I, 3 minus I. And the eigenvalues are a complex conjugate pair, right? That will always happen when you have complex roots. For a polynomial with real coefficients, your roots will come in complex conjugate pairs. So one is 3 plus I, the other is 3 minus I, just negating the imaginary part. But notice that the eigenvectors also can show up, also will show up. So it happened here, but this will happen every time for a real matrix. The eigenvectors also are complex conjugate pairs. You see, 2 minus I became 2 plus I. So knowing that might also help save you some work. Okay, so that's it for this example. But how does that help us with understanding what's going on here when we apply this to the smiley face? Well, what was I doing before? I was like, sorry, I was drawing some lines to indicate the directions of the eigenvectors, right? But here, my eigenvectors are these, which have some complex entries, right? Which way do those point? How do I draw those vectors here? Well, I can't. Those vectors don't point in any direction in this space, at least. They have an imaginary component, so if you're going to depict them somehow, you need to introduce some additional dimensions, which this smiley face doesn't even know about, right? This guy's living in 2 dimensions. So if you just think in terms of the sort of geometric problem of are there directions that this linear transformation 1, 5 minus 1, 5 preserves? Are there directions where if I put the eyeball along that direction, then it'll just get scaled out? The answer is no, there are none, because those directions correspond to real eigenvalues and real eigenvectors. And this matrix doesn't have any. So if you lived in a time before complex numbers were invented, which actually isn't that long ago in some sense, then if you lived in that time, you would look at this matrix and you would say it simply has no eigenvalues. Right, you would say, well, when you try to find the eigenvalues, you end up with the square root of a negative number stuff, and that's nonsense. There's no solutions to this, so this has no eigenvalues. So I've put many eyeballs on the boundary of this smiley face, and you can interpret what we're saying here as saying, when you apply this transformation, there's no one of these eyeballs that just gets scaled out from the origin. Everybody gets rotated to some extent and changes its direction. So probably I should make these have different colors so that you can follow along. But maybe what's actually easier is to look at a simpler example of a matrix with complex eigenvalues and eigenvectors. How about just a 90-degree rotation like this? If you get the characteristic polynomial for this matrix, it'll be the determinant of this, which is lambda squared plus 1. And then what are the roots of that? Plus or minus I, right? Are the roots of this polynomial. So this has no real roots. So in the modern times, we say this has the roots plus or minus I, but if you lived in a time before complex numbers were invented, then you would just say this has no real roots. This matrix has no eigenvalues. And now if I come in here and I type 0, 1, minus 1, 0, and I apply this, then it's just getting rotated by 90 degrees, right? See? So of course none of the eyeballs on the perimeter are getting preserved in their direction, right? Everybody gets moved. Nobody just gets scaled along the origin. So there are no eigenvectors, therefore no eigenvalues. But if you just allow yourself to include complex numbers, even though you started out with something that had no complex numbers in it, complex numbers kind of force their way in. And if you just allow this to happen, then the wonderful algebra of sort of this situation where you could say, oh, now I have a very nice simple way of describing how A behaves. It just does this and that to the individual coefficients in a decoupled way. All this stuff, the decoupling of how, sorry to keep flipping around, I'm trying to find this page. So the decoupling of how A operates on, of how A's action affects coefficients, decoupling that still happens if you just allow for complex numbers to show up. And that is really useful. Because as you will see, it'll turn our coupled systems of differential equations, it'll help us turn those coupled systems of differential equations into individual not coupled differential equations. And we have also seen that if we have real complex solutions to differential equations, then we can just take the real and imaginary parts to get ourselves real solutions. So we're actually totally okay with ending up with complex solutions.